Harshvardhan, it is slide is visible.
Yes, sir.
Yeah. Okay. Good morning to all of you. Uh, so last times we have discussed the laser threshold. We have seen why laser is a threshold device. Maybe it is a gas laser, maybe it is solid lasers, maybe dye lasers, or maybe semiconductor lasers. But all are threshold devices. That is because first threshold condition should be reached, then only you will get the ledging action, right? For that, what we have seen actually, there is a gain and there is a loss, right? When gain is equal to loss, that's what it is mentioned here. You can see it here. When gain is equal to loss, then only you can have the threshold conditions, and after that, when the gain just exceeds the loss, then you will get the ledging action. And what are the how gain is obtained? Gain is obtained by the medium. In general, we have seen this. There are two mirrors are there. One mirror should be of 100% reflection nearly, and another is 9 to 95% reflection, not the transmission. Only 5 to 10% light uh, comes out from the laser source, right? 5 to 10%. So this is the threshold conditions, and the losses we have seen, maybe transmission and absorption loss, maybe diffraction loss, maybe absorption loss and scattering loss within the mediums, and mode conversion loss. And so these are the losses. When the gain equal to loss, the threshold condition, when gain just exceeds the loss, will get the power difference will be there. That will be treated as the optical output. That will be the actual output. That is 5 to 10% of the light that is coming out, right? So with this concept, now we can find out these threshold conditions, and we can find out this what is the gain at threshold, which is the most important parameter in all lasers, particularly for semiconductor lasers. So we're focusing on semiconductor lasers. So let us see how this expression is same for all the lasing devices, but since we are considering the semiconductor lasers, so we'll see how actually current threshold current is determined, which parameters actually determine the threshold current, right? So to get this threshold, I mean gain, optical gain at threshold, so let us consider the same things. Consider resonators, two resonators at resonator, and laser is you see light is produced in a laser device within a resonator. It's a resonator. It's an optical feedback is there. A resonator means it's an oscillator. It is an oscillator because here positive feedback is here. Right. So here in this case, you see whenever light is emitted, I told you it will be reflected back and forth, and a portion of the light is reflected, is transmitted. That is the lasing output. So initially there will be stimulated spontaneous emission, and these photons, when they strike the excited electrons in the upper energy state, then there will be stimulated emission. Right. So you see the photons, they will forward in these directions. Next, it will be reflected by this mirror. Next, it will enter into the mediums. Next, again, it will be reflected by the second mirror, and it will be reflected back. So in this way, there will be increasing in the power. Because more stimulated emission will be there, more power will be there. So power per unit volumes, that we can write it. If I is the intensity present initially, then it is if the z direction, it is d I nu upon dz at certain distance z, rate of change of intensity. I mean change of intensity with respect to distance. It will be proportional to the intensity present. For the more photons present, mean more stimulated emission will be there. So d I nu upon dz, that is proportional to I nu z. At that point, what is the intensity? This is power, this is volume, this is intensity, this is power. What is volume? dz. Actually, unit cross section, if we just consider dz, the length, a section, if we consider thin segment of unit cross section, then dz will be volumes. So du I nu I dz, that indicates actually power by volumes. So this can be equal by constant of proportionality to g nu. G nu, you see it here, this is g nu times I nu z. Now, if you solve these equations, simple differential equations, if you just solve it, I nu z, it will be I nu 0 e to the power g nu z. I nu z equal to 0. Initial intensity, it is I nu 0. So this you will get it. It's very simple. Just integrate it, you will get it. This ones, right? And so it is this one, but you see it is gain. this G nu actually it is the gain coefficient because power is increasing, so that is the gain coefficient. Now the question is when the already have seen it when the light propagates through the mediums, there will be losses also. So you have to consider actually loss factor, that is the effective absorption coefficient alpha bar nu absorption coefficient, including absorption scattering everything. If you consider that the loss factor alpha within the mediums, then I nu 0 will be equal to e to the power G nu Z minus alpha bar nu into Z, right? Because it is loss, so it will be minus alpha bar nu, right? So ultimately, what do we get it? I nu 0 e to the power G nu minus alpha bar nu times Z, right? At a certain distance Z, right? Now, if you consider a complete round trip, say suppose here, if you start from here and next it will go the second mirror, next it will come at this point. It's complete round trip. If you just consider, you see it here, it is shown here, just passive laser. For the time being, consider passive one. Here, two mirrors are there, and intensity is reflected back and forth. Light is back and forth. So initial intensity is I0. Here the reflection coefficient is R1. This mirror reflection coefficient is R2, right? So I0, this is in Z equal to 0, I0, this length of the resonator is L. So I0, when it is at the second mirror, it will be I of L. That is intensity at distance L, it will be I of L. How you can estimate the I of L? From the previous equations, you have seen it. You see it, you put Z equal to L, you'll get it I of L, right? So it is now if you consider one complete round trip from here to here and here to here and again here at this point, then it will be I of twice L will be there, complete of twice L. So IT twice L will be I nu 0. Next, you see here two reflection coefficient will be considered R1 and R2. That is because you see I0 when it is reflected back, that will be R2 times I of L, and 1 minus R2 will be transmitted. Again, this beam, when it just before this one, it will be R2 times I of twice L. This is R2. This is R2 times I of twice L. Just before touching this mirror, when it just reflected, then it will be again reflection coefficient will be considered. So it will be R1 R2 into I of twice L, and the transmitted component will be 1 minus this one, 1 minus R1, 1 minus R1, sorry, 1 minus R1 times this one, 1 minus R1 times this one. So this is actually the final intensity here after reflection. So that's what, if you see, consider this I nu twice L, that will be you see it here, I nu 0. So two factors should be considered, R1 R2 times the times that expression. So I nu 0 into e to the power G nu minus alpha bar nu times twice L. Z will be twice L. So you're substituting this here. So that is the after one complete round trip, that is the intensity. Now at the gain, so what will be the gain now? Initial intensity I nu 0, final intensity I nu twice L. So it will be the ratio will give you the gain. And at threshold, what's this one? The both must be equals, because there will be losses, absorption, etc. Absorption, scattering, etc. Those things will be there. So at threshold, power after complete trip will be equal to the power, initial power. So in terms of intensity, I nu of twice L equal to I nu 0. Substitute these conditions here, you will get it. That times G nu, we are explaining G threshold. So G threshold will be now, just substitute the value of G threshold here and put this I nu twice L equal to 1. Then you see it here. You can see it, this G alpha bar, and if you take the see a log, so it will be it will be cancelled. So so 1 by twice L, 1 by twice L will be there, right? 1 by twice L. This will be equal to 1 by twice L times R1 R2 log of minus 1, because R1 will be in this side. This is 1, so it will be this one 1. So it is this one. So G threshold now will be equal to alpha bar nu plus 1 by twice L log of R1 R2 minus 1. So that is actually the gain at threshold. This is the most important parameter for laser design. Once you design the laser, you have to consider this what should be the gain at threshold. And once you know this gain at threshold, this resonator parameter, then in terms of current, you can find out this G threshold actually equal to beta times J threshold. So J threshold is the for semiconductor laser, it is the current threshold at current density, I by A. So just G threshold, you can write it here. So this is the factor that depends on the materials, which materials you are choosing. So if you know this factor, then you can find out what is the threshold current for a particular semiconductor lasers. So this is the most important expressions. So anybody, if you have any questions, you can ask. Anyone? कोई किसी क्वेश्चन है तो पूछो.
No, sir.
Okay. So if you know this G threshold, so numerical problems generally also given, find out the current density if you have the other parameters, right? I mean current threshold current, generally it is asked, threshold current, or maybe if threshold current is given to you, you have to find out what will be the reflection coefficient at the two mirrors. Initially, generally, R1 or 2, see these are very small differences here. Sometimes R1 or 2 can make equals, right? In its calculation purpose. Next, slide it is changed. Right, there different aspects are there. We are not going the details of laser design. If you see any laser book, you can have the details of it, right? But this is sufficient for us for the time being. If you know the threshold current for a semiconductor lasers. Okay, next parameters, you see the structures. Now, what will be the, so we have seen this laser lasing principle, lasing some parameters that are responsible for lasing output. Now we see some structures. What is the structure? In LED structure, generally we have seen this edge emitting type and surface emitting types. Here, almost similar structure is here, but you need feedback. So that based on the feedback, there will be two configurations are there. One is Fabry-Pérot types laser diode, and that is distributed feedback laser diodes. In Fabry-Pérot type laser diode, it is based on Fabry-Pérot interferometer. What is Fabry-Pérot interferometer? You can see there are semi-transparent two glass plates are there, and if the light incident, it will be reflected back and forth. It's a partially reflecting two plates. Then so each reflection, there will be a transmission of light will be there. And if you have a condensing lens, then you can have a fringe patterns. So this is actually the Fabry-Pérot interferometer. There will be two partially reflecting mirrors are there separated by distance. And if you have the interference pattern, that is called the Fabry-Pérot interferometers. It's a multiple reflections. Other interferometer are there. There are only two, one beam and two beams, two beam interference, but here multiple beam interference, this Fabry-Pérot interferometers. So based on these things, the laser structure also has been fabricated. Laser structure has been considered. Laser structure is based on this Fabry-Pérot interferometer, particularly for the first type of lasers. So in this case, you see these layers are there that we have seen it. That we have seen it. Say there are different layers are there: metal contact, substrate, next 3 layers, next will be again metal contact, maybe heat sink, etc. Those things will be there. So those are common, but only thing is, so I'm showing just 3 layers here. This is DH layers, light confinement layers, and this is the active layers, active regions. So in the middle layer, light is coming out. But here, the difference is this with the LED is that here end surfaces are coating with dielectric materials so that they can behave as mirrors, and in that way you can have the feedback, the optical feedback, you can have it. That is the main difference between the laser structure and LED structure. Of course, this feedback can be not only maybe end to end, maybe throughout the materials. That will see it for distributed feedback. So anyway, for Fabry-Pérot types, at the end surfaces, coatings are provided. This dielectric coating is there to get the feedback effect. Right. Other things are common to LED structures is the two layers or carrier confinement layers, and this is the active layers. Right. So this is the Fabry-Pérot layers. Next, distributed feedback layers. In fact, if you need very high coherent, high monochromaticity lasers, I told you lasers coherence can be spatial coherence, temporal coherence. Temporal coherence related to high monochromaticity. Right. I told you if you want the light is emitted, some delta lambda always will be there, right? Though it is red, perfectly, if you perfectly red, then the single line will be there. But some spread will be there. That is because of this multimode behavior. But if you have just DFB laser, feedback layers, it will be highly coherent. Almost near delta function, you can have it. Very narrow delta lambda will be there. This delta lambda is quite for LED, it is much more wide. For LED, it is much more. This delta lambda, it is to maybe 100 nanometer. But in case of laser, it can be say 2 to 10 nanometer. Even distributed feedback lasers, it can be less than 1 nanometers. Right. So very narrow line width can, I mean, almost single mode lasers you can have it in case of DAB lasers. So what is the structure here? Instead of end, all are same things. 3 layers are there. You can see it here: light confinement layers, active layers. This is the middle layer is the active layers. You can see it here. Something. If this is the active regions, actually something wrong is here. The light will be coming out from these layers. I mean, something you can correct it. This ones, right? This is the active regions actually, right? Light confinement layers, and this active from the active layers. Light will be coming out. Here it is, not from these ones. Anyway, it's quite clear. I mean, from the active layers you get the light. The main difference is you see here some corrugated structure is there. It's a wavy structure is there. This structure actually called grating structure. In fact, because of it's a Bragg grating is created. Bragg grating, Bragg condition is satisfied. What's Bragg conditions? It is lambda by B equal to 2 n effective lambda by K. This is the Bragg conditions. Right. Just let me check the relation. It is okay. Bragg conditions. Okay, is the order of gratings. Yes, this K is not the 2 pi by lambda. It's not that once. It is not a proportional constant. This K is the order of gratings. Actually, order. If you know the gratings, there will be first order, second order, third order, etc. So generally, K for Bragg grating, it is the 1 K equal to 1 order of interference or order of the gratings. Right, order of grating. It is not the 2 pi by lambda, this K. So it is the Bragg conditions. This Bragg conditions to satisfy it should be the Bragg gratings, right? I mean, only first order diffraction you can have it, right? Because of these things, grating structure, corrugated structure, you can have very less number of modes, right? Number of mode and coherence will be very high. Temporal coherence will be very high. So it is instead of and feedback will be throughout the structure. So it will be reflected back from the grating structure each point. So earlier you have seen this Fabry parrot, only end surfaces you are getting the reflections, but here throughout the materials always there will be reflections. So in fact there will be standing wave patterns perpendicular to these things. And based on these things, the resonance will be, resonance will be there, and coherence will be very high, right? So that is the concept of this, the DAB lasers. Okay. There are other structure also there, like distributed feedback lasers. You see another structure is here. There is distributed Bragg reflector, where both sides getting structure is there. In between there is no getting structure. Other things remain same. So that is distributed Bragg reflectors. And one more structure is there, distributed reflector, where active passive regions are there. Distributed reflector lasers. Active and passive. This is active layers. Active layers is not throughout the, here you see active regions throughout the device from end to end. Active region is here. Here also active regions throughout this one. Only the getting structure is not throughout. See that differences between among the structures. Here feedback is throughout the device, but here feedback is only at the ends, and here feedback is throughout the device, but active passive is limited. Here active regions, this one, rest is the passive regions, right? So this is done actually to increase the efficiency and high output capability. So these are the different distributed feedback type lasers. One will be this distributed feedback lasers, another is distributed Bragg reflector, another is distributed reflector. Distributed DBR means distributed Bragg reflector, and DR means distributed reflector lasers. Distributed reflector lasers, DR, reflected laser. So these structures are there to increase the efficiency and high output capability. And efficiency means high coherence, you can have it. Right. So these are the different structures. Quick structure के बारे में किसी का क्वेश्चन तो पूछो. If you have any questions, किसी का कोई क्वेश्चन है तो पूछो. No, sir. Okay. Then you see modes. I have mentioned now modes are there. Modes are important when you deal with the laser device. Modes are to be just like fiber. You have seen these modes are there. T modes, TM modes, hybrid modes. Those modes are there. Since laser is a resonator, because light is produced within a resonator. Resonator means oscillator. You have seen it because of the feedback. So here also modes are being generated, and these modes are actually classified into three types. Of course, two types. Most of the lasers, but in semiconductor generally it is three types. So it is transverse modes, lateral modes, both are almost same, some treated as the same. Anyway, you see it here, there are three modes, three types of modes: transverse modes, longitudinal modes, and lateral modes. Right. Transverse modes, this related to this beam profile, beam width, etc. Laser beams, they decide these ones. Longitudinal modes, delta lambda. I told you delta lambda is the narrow. So the narrowness of delta lambda or the value of delta lambda will be determined by these longitudinal modes, right? Line width, monochromaticity, etc. So line width means delta lambda or delta nu, right? So those are being determined by the longitudinal modes. And lateral modes, that is the lateral profile of the beam output. It's almost same as these transverse modes, right? So these are the different modes are there, and you see for Febipyr generally is in case of laser. It is say since it is not a waveguide, so here actually modes are labeled as TEM00. Right. Actually, TEM MN cube in rectangular coordinate systems, and in cylindrical coordinate systems, it is TEM PL cube. PL cube. Right. This MN first two suffixes M and N. This represents the transverse modes, and this cube, this represents the number of longitudinal modes. This cube is generally quite large, maybe 200. But Mn generally of first few integers, maybe 00 for Gaussian mode. Say it is the Gaussian distribution. For Gaussian distribution, maybe just the fundamental one TEM00. If higher modes are there, then say the center is bright. Then if it is TEM01, there can be some dark ring will be there. One dark ring will be there like this. It's like fiber also that you have seen it. So these are the different modes are there, right? Okay, so in lasers we have generally two types of modes are there: transverse modes and longitudinal modes, right? These modes will determine the spatial coherence as well as the temporal coherence. Temporal coherence is determined by these longitudinal modes. Spatial coherence is determined by the transverse modes or lateral modes. Now, in a Febipyr resonators, you see if you write this one, the grating equation, or this is the interference. It's not a grating; it's an interference. For any interference, if it is, then it is actually twice NL equal to M lambda or Q lambda 0. So actually twice NL sin theta equal to Q, let me say theta normal. If you just consider, then theta 90 will be 1. So it is twice NL equal to Q lambda 0. That is interference relation for any resonators, for any interference, two beam interference. So here it is actually you see it N represents the refractive index of the mediums,
L the length of the resonator, Q is the order of interference, lambda wavelength of light used. So lambda 0, you see it here, twice NL by Q, right? And if you convert in terms of nu, then it is nu equal to nu equal to C lambda, right? So from that you can have it C cube nu equal to C cube by twice N and L, right? So actually frequencies that will be sustained within the cavity, ledging cavity, that is actually nu cube, right? Nu 1, nu 2, nu 3 in this way. But you see all the frequencies will not be sustained within the ledging devices, because you know threshold condition is there. Is threshold condition, so many frequencies will be there within the gain curve, but only the frequencies that will be sustained within the cavity, those are above threshold. You see, other one will be other loss will be high for the other frequencies, so they will not be sustained. So now the question is, if these modes are there, then what will be the intermodal spacing, or how many modes are there? How can you calculate? Actually, this frequency means it is the longitudinal modes. Actually, you are considering with the longitudinal mode, which is most important. So if you know the intermodal spacing, is a spacing between two modes, then you can calculate. If you know the total line width, delta nu, then you can calculate how many modes are there in the ledging device. So for that, you see there are the different oscillation frequencies, nu q, nu 1, nu 2, nu 3, etc. So if you consider the intermodal spacing, that is say for any between spacing between two frequencies, then that will be nu q plus 1 minus nu q particular order. So that is actually delta nu. So that delta nu equal to, now if you just nu q plus 1, if you just put it nu q plus 1, and another is nu q, the q plus 1, and another is nu q, c q by this one, then CQ, the first term will be cancelling, will cancel, and the only q will be absent, then it will be C by twice NL, C by twice NL, this will be there. So the delta nu you can find out if you know the resonator length, the refractive index, then you can find out the intermodal spacings. So once you know the intermodal spacing, then you can calculate the number of modes. Number of modes will be, if you know the line width. What is the line width? Is for I told you, whenever source emits light, some line width is here. Delta lambda will be there, or delta nu is there. So this is the line width, and this is the intermodal spacing. So if you just divide it, you get the number of longitudinal modes. This is in terms of frequency. This also can be in terms of lambda. I mean, since the relation is here, delta nu by nu equal to delta lambda by lambda. So you can find out delta lambda equal to lambda square by twice NL. Sometimes in the numerical problem, it is also given, not in terms of nu, in terms of lambda. Suppose you are given, say laser is emitting, say 800 to 900 nanometer. In this range, where light is emitting, that means delta lambda will be 900 minus 800, 100 nanometer. You can find out like these things. That will be the line width, delta lambda. So once you know the delta lambda, small delta lambda, then intermodal spacing can be calculated from the emitting wavelengths, center wavelength, lambda by twice NL, right? From this you can find out delta lambda, and from this you can find out the line width. So that is delta lambda, say then delta lambda by capital delta lambda. You will keep the number of longitudinal modes. The same way it is in terms of frequency also. You see it. किसी का कोई क्वेश्चन है तो पूछो इसके बारे में, ये बहुत इंपॉर्टेंट है, इसमें क्वेश्चन बहुत सारे क्वेश्चन आ सकते हैं. बोलो, समझ में आया तो बोलो, नहीं समझ में तो बोलो. कोई किसी का क्वेश्चन है तो पूछो.
नहीं सर.
Number of longitudinal modes कैसे डिसाइड किया जाता है? From this you can have it. In Kaiser also you can have it, maybe a little bit in other way, but these relations are there. You can see it. What I've shown you how to calculate this number of longitudinal modes. Not exactly maybe this way. Slightly different forms. Let me forget in what forms it is here. These things are there, delta lambda expressions are there, right? Expressions are there. The concept wise, if you just clear it, then I think it will not be a problems. The same different notations are there only. You can have it. Okay. Then you see, so modes we have seen it. Now see the modulations. You have seen this LED also. Whenever you modulate their output, there is also modulation rate is limited by the diffusion capacitance. Here, when you modulate the laser diode, the factors that should be considered is a spontaneous lifetimes, stimulated lifetimes, and photon lifetimes. The three lifetimes are spontaneous lifetime. When the electrons are excited, they will come to the ground state without any external stimulations. So that is the lifetimes. The lifetime of that spontaneously emitted photon, that is the spontaneous lifetimes, that is tau sp, that is of the nanosecond. Stimulated lifetimes, when you see here that we have seen it, when electrons are forced to make a nano transitions. Right, that time the lifetimes of the photon, that is not the photons, lifetime of the carriers actually. These are the lifetimes of the carriers, right? Carriers. So this is the spontaneous lifetimes, nanosecond. This is stimulated lifetimes when the carriers are forced to make a nano transitions, right? So obviously here it depends upon the intensity present within the cavity, and in this case the spontaneous lifetime will be determined by the semiconductor band structure, doping, etc. All right, so that will determine the spontaneous lifetimes, and the stimulated lifetimes is determined by the optical intensity present within the cavity. And another lifetime is which is called photon lifetimes, is a lifetime during which the photons reside in the cavity before being escaped. You have seen this in a laser device. You have seen it. So this is the two mirrors, and in between medium is here. After back and forth, actually light is coming out. After when the gain exceeds the loss, then light is coming out, right? So it is the lifetime during which the photons resides in the cavity before being escaped from the cavity. This is the cavity, resonant cavity, right, of length L. So that is the photon lifetimes, and that is of the picosecond. Stimulate also of the picosecond. But since spontaneous lifetime of the nanosecond, so some delay will be there. Between the application of current pulse and the onset of radiations, right? So because immediately you will not get the emission of light, some delay is there. That delay depends upon depends upon the threshold current, also depends upon the current pulse, threshold current, as well as the bias current, right? If this delay is minimum, then you see it will be modulation rate will be very high. Otherwise, modulation rate will be slow. Modulation rate of laser is very high. That is because it is biased with some value IB. It is not the zero bias. It's a diode can be without bias, can be modulated without bias, or it can be, some drive circuit, some transistor, etc. Those things will be there. So it can be operated under zero bias, or it can be operated under certain bias current. Initially, some bias current will be there. So if you have some bias current, then it will be operated very near to the threshold. Then modulation rate will be very high. That is the main concept of modulation. How can you modulate? How can you increase the modulation rate of laser diode? The question is this. Now here you can see it. Example in this figure, you can see it here. Here for normal lasers, say normal lasers, when you apply the current, say power will increase, and this some fluctuation is that is because when the gain is clamped at threshold, it will be something like this: population, depopulation, population, depopulation. These things will be there. Some spikes are there, right? And also you see it here. After application of the current, after certain time, this is the time intervals. After this, you are getting the output. So this delay is there. This delay can be minimized. This delay can be time delay can be minimized if you apply some bias current in a laser diode. Bias current, you see it here. This bias current can be at zero levels, or current at zero levels, or it can be very near to threshold. So if the bias current, bias current, if it is very near, this is threshold levels, right? the threshold levels, then you can see this curve output. You see it here, somewhere here. So this is now the time delay. You see this time delay. Right. So time delay is now reduced because of the application of bias current. That's what it is there. Okay. What also these spikes can also be minimized here if you apply the bias current. I can so we can see it also how this the bias current mathematically it can be shown also. Bias current can reduce this time delay. In turn, it can increase the modulation rate. How? You can see it here. Suppose you are applied a current and you are applying some current that will reach to a value of I, right? So whenever I is there, current, because of the injection of current, excess carriers will be generated, that we have seen several times. So in LED also. So excess carriers that is generated dN upon dt in semiconductors, that will be J by QD minus N by tau. This J by QD, that is the number of carriers generated, and N by tau is the number of carriers recombined. Right? Because of recombination, light is coming out. So that is the depends on this. This is the rate of excitations, right? Excess carrier concentration, rate of excess carrier concentrations. Now, this can be solved with the also with the initial conditions are there. This can be solved with the Barnard conditions. In the initial conditions that at t equal to 0, initial conditions would be say I0 times tau divided by Q into D, right? This I0, it is the bias current, right? I0 initially some bias current is here, so I0 is the bias current, right? And after application on this bias current, when you apply the current, it will reach some value, that is a value of I, current applied, right? Current that is that will be that will you can have it after the application of current above bias. This current is I. So you see at threshold, excess carrier will be N threshold, that is N TD, TD, N threshold or at time TD, that is at the threshold. That will be J threshold by tau by QD. These are the initial conditions, right? Now, if you solve it, this can be solved with integrating factor. It's very simple, or by using Laplace transforms. You will get this one NT. If you find out the NT by QD by tau, you can have it J minus J0 e to the power minus T by tau. You can have it, right? Now at threshold, if you have condition this from this equation, that is NT will be N threshold, AC N threshold. So it is N threshold QD by tau. That times this T will be TD. So if you put this at threshold, so J threshold will be J minus J0 e to the power minus TD by tau. So this will get it. So if you just solve it for TD, time delay, what you can have it, just simply take the log and you'll get it. TD will be equal to tau log of J minus J0 divided by J minus J threshold, or in terms of I, or I by A. So it will be tau log of J minus I minus I0. It is I minus I0 by I minus I threshold. So there I0 is a bias current, and so you see it here. If I0 approaches I threshold, if I0 approaches I threshold, then this will be 1. I minus I threshold, this will be 1. That means it will be 0. That means TD will be 0. That means if you apply the current very near to the threshold, I0 means I0 approaches threshold. That means if I0 bias current, if it is very near to the threshold, then I can have high modulation rate. That's what it is shown here. You can see it here. You can bias current can be somewhere at the 0 or 0 bias current. Now, if you're increasing the bias current, somewhere it is, if it is very near to threshold, then this delay will be far less. TD will be minimum and time delay will be minimum. That means you can have very high modulation rate. So that is a concept of this the modulation rate. Any questions regarding these modulations? कोई किसी क्वेश्चन तो पूछो.
No, sir.
Here you see this threshold current, what I'm saying, it can be temperature dependent also. Generally not can be, it is temperature dependent, and in that case the expression is here. I threshold T equal to Iz into to the power T minus T0. At certain temperature T, the T0 and Iz, they are the constant terms. So if you know these constant terms, then you can find out at temperature, certain temperature, what will be the value of I threshold. These things are there in Kaiser, you can see it. Also, when you deal with the lasers in optical fiber communications, you can face with these problems: speckle noise, mode partition noise, reflection noise. What is speckle noise? Speckle noise is a whenever laser, if you use a laser, if you in a wall, if you just illuminate it with the laser, there will be some, you can see some granular spots are there. You can see some twinklings are there. Granular spots, that means dark white points are created. Those are actually speckles, right? Granular spots are there, dark white spots are there. These are called the speckles. So how the speckle is within the fiber? Suppose in a fiber light, laser light you have launched and is propagating. Now, if there is a break, or something like that, different media is there, then also connector is there, splice is there, then this speckle noise will be created, right? And this will degrade the signal to noise ratio. That is the speckle noise or the coherent noise. There can be another noise also, mode partition noise. You see, you have seen this certain number of longitudinal modes are there, and there will be intensity fluctuations whenever mode conversion take place from one mode to another mode, when the power is transferred from one mode to the other mode, right? So because of these intensity variations, there can be a degradation in the signal to noise ratio. So these things are to be taken care. Another thing is reflection noise. Whenever some break is there or some connectors or splices are there, then a portion of light is reflected back into the source, and that will create the noise. So that will create the noise spectrum, right? If the lasing emission spectrum falls within these noise spectrums, then it may destroy the laser device. So take a care should be taken to isolate that reflection of light. So that is the reflection. Sometimes up to isolators are used in between laser and fiber, up to isolators. So these are the different types of noises that must be considered while dealing with the laser sources. I think that completes my lasers. So anybody, any questions regarding lasers today class, you can ask, otherwise stop it.
No, sir.
Rest, others? बाकी लोग सो रहे हैं क्या? किसी का कोई आवाज भी नहीं आता है. Vishal, are you listening? No. Tanisha, are you listening?
Yes,
Tanisha, are you listening? No. Sinsat, are you listening? Like that, all should get 0. Then probably will listen. Priyansh, no. Komal, no. Susmita, no one is listening. Rohan, no. Avinav, Rohan is active. Others are passive. Avinav, actually total, I think 19 plus maybe 30. 30 students there. Okay, it's up to you how much you can cope with it. Okay, then we'll meet again at one thing. Harshvardhan, quiz will be in the next week. Already will I have discussed with Soumya madams. I mean section B. So next Friday quiz will be there. Right. Next Friday. Next week Friday. Okay.
Yes.
Timing, it's up to you. After 6, any times you can decide. But you tell me earlier so that before my posting, you must mention it. The changes will be a problems, right? Because
Yes,
I have
sir,
some other. You discuss yourself, or any times we don't have any objections.
yes.
Friday, okay. Okay, then again we'll meet
Thank you, sir.
12 o'clock, okay.